Alright, so in this video I'm going to take a look at the first section of our Year 12 mock exam on mechanics. I'm going to start off with a projectile motion question. We've got a scenario of cricket, so we've got a ball hit at 30 degrees to the horizontal, which we can see over here on the right hand side of the setup over here. So that's where the batter is. It hits the ball at 30 degrees and it says it reaches the field without bouncing, so we can see it's not bounced anywhere in this region here, and it was caught at the same height, so effectively there's been no gain in GP or height or anything during this, and initially the effective air resistance on the cricket ball is negligible. Okay, so the first thing I want to do is calculate the vertical speed of the ball. So we know its speed along an angle of 30 degrees is 22, so we can construct our vector diagram like this. We want the vertical side, so we want this one over here, so we essentially need to use sine because it's opposite to the 30 degrees, so 22 sine 30, and that gives you an answer of 11 meters per second to two significant figures. Really straightforward. Okay, so next we need to show that the ball was in the air for about 2.2 seconds. So the key to this is recognizing that when it returns to the ground, its displacement is going to be 0. Its initial speed is going to be 22 sine 30 because the time in the air is only dictated by the vertical component velocity. We don't know what the final speed is. Well, we actually do, but we haven't been given it. You know what the acceleration is, and you don't know what the time is. So the equation we want is this one here, because it doesn't contain v, as we don't have v. We put s equals 0, which allows us to cancel two of the t's across, because that is equivalent to the solution t equals 0. Rearrange, and you get 2.24, which you can simplify to 2.2 seconds. The other way you can solve this is actually, because there's no air resistance, you know, the speed at the end will be equal and opposite to the speed at the start because it returns the same height. So you could have done this with v equals u plus at, where you put v is minus 22 sine 30 and u is plus 22 sine 30. Again, that would work. You can also find the time to reach its maximum by putting v equals 0 in here. You would find the time till it reaches its maximum, and then doubling that would again give you 2.24. So there's a few ways of solving this, but I saw a lot of people with this put in u is 22 and v equals 0 and solved and found 2.2, but the nice examiners who constructed this paper were obviously very smart because they found a way of essentially tripping people up and getting the same answer, which is brilliant, but don't fall into their trap. And then, how far did the ball travel horizontally before it was caught? So again, this time we need our horizontal components. So before we've been working with our vertical components. So again, I'm going to use this equation here, but the weight force acts vertically, so the acceleration in the horizontal direction, because air resistance is 0, is going to be 0. So we just get this nice simple equation here. We want the horizontal component of velocity. The time it's in the air gives us 43 meters. Again, none of those parts were at all complicated. These should be absolute banker questions. These are really straightforward. Okay. All right, so this next question was absolutely brilliant because this exposed a lot of you who cannot get the idea of your head that the mass has any impact on anything. Okay, so if we think of it in terms of first of all working out how the maximum height would change. So if we neglect air resistance, what you have is essentially kinetic energy being transferred into GPE. So what we can see is without air resistance, actually mass has no effect on the final height reached. Okay, so a lot of you picked up this first one about recognizing the tennis ball, because it has a lower mass but the same speed, will have a smaller amount of kinetic energy. That's absolutely correct, and you do need that as part of your explanation as to what happens here. But that does not mean it reaches a lower height. I don't know how many times we can go through this and you still not pick this up. Mass has no effect without air resistance. So what that tells you is, because it shouldn't have any effect, if the tennis ball has had a different maximum height in a different range, that tells you it must be to do with air resistance, the difference between them. Okay, so that's where the next parts come in, which a lot of you did not get. So they will experience a similar air resistance, or actually I would expect the tennis ball would experience a slightly larger air resistance. If you think of what a tennis ball looks like, it has a large fluffy coating on it, which is very likely to increase the air resistance. So if, say, for the sake of example, they experience the same air resistance force, the rate at which they lose energy will end up being the same if they're experiencing the same force. So if they're losing energy at the same rate, but the tennis ball has a smaller initial kinetic energy, that means it will be a much shorter amount of time to essentially get rid of all of that kinetic energy. And so the result of that would be you end up essentially bouncing before you hit the fielder. You don't reach the fielder because essentially you've lost all the energy faster. So that's what's going on here, and it's kind of helpful to have a look at how that looks on a diagram. So if you're losing kinetic energy at a faster rate, you can see you're not going to reach the same maximum height as you do before, because your air resistance term is essentially taking away some which could have been transferred into GPE. And you can see if you have a shorter flight time, what that's going to result in is you essentially bouncing sooner. So if you don't get as big a maximum height, you're going to have a shorter flight time, which gives you a shorter range there. So that's what's going on in this particular question here. But I cannot stress enough that without air resistance, mass has no effect on maximum height if they have the same speed. I don't know how many times I can say it. Okay, so that's projectile motion. Let's move on to the next question, looking at moments. So first off, loads of people only got 1 out of 2 for this. This is a basic definition. Everyone should have got 2 out of 2 for this. So a moment is the product of a force and the perpendicular, so that's the first key thing you should talk about, perpendicular distance between the line of action of the force and the point moments are taken about. So if we're taking moments about here, and your force, I don't know, is here, your line of action is this one. So essentially it just runs parallel and in line with your force. So the perpendicular distance is that one, like this. So it's the perpendicular distance between the line of action and the point you're taking moments about. There is no way of getting around to defining this. That you just have to know this definition. Okay. So then what we've got is a scenario. So we've got a diving board. So if we have a look at if you think so, it tells us it's supported or resting on a cylinder C. So there's going to be a reaction force acting upwards from the cylinder on the diving board. You have the weight force here from the center of your diving board, and there would actually also be a reaction force, some sort of upward force which they haven't shown you on the diagram, but would be there. So first of all, by taking moments about A, which makes sense because we don't know what R is, but they were quite nice to you in this case because they told you where to take moments about, explain why the force P must be greater than the weight W. So if we take moments about A, R is not going to be a factor, so we only get these 2 forces. So we can see P is this distance away from A, whereas W is this distance away from A. So a lot of people with this recognize the distance, or the perpendicular distance of W is bigger, therefore W has to be smaller. But they gave no reason why that should be the case. So you can't get away with that kind of thing at A level. You need to actually explain why that works. And the reason is, because it's in equilibrium, the moment of P must be equal to the moment of Q. That's the only reason the distances would play a part at all. And then the second part is then about talking about how the distance affects the force, but you need to explain why. Okay. So in terms of the next part, state and explain what would happen. Well, so what would be the effect on force P of a girl walking along the board from A to B? So let's just quickly redraw. So we still have the reaction force there. We have an upward force P, and we have a downward force W. And what we're doing is we're adding in another weight force. So when the person, or the girl in this case, I think it is standing at A, that would have no effect on P because the moment of her weight force would be 0 about A. So we can see that P would be initially the same. However, if we then move her along, so she starts walking from A to B, we can see that this would add another clockwise moment, because we can see this one and this one are going clockwise, and P is the only anti-clockwise. So if the system is going to stay in equilibrium, it's a diving board. If it suddenly collapsed when you walked on it, it wouldn't be a very good diving board. So we can see that the moments must still be in equilibrium. Therefore, P, it hasn't altered its distance, so it must increase in force to allow it to increase its moment to counterbalance this. Then, as the girl walks along, the moment of her weight force is going to become bigger and bigger and bigger about A. Therefore, the force of P is going to get bigger and bigger and bigger. And because her moment's going to increase linearly, the force of P would increase linearly. So that's the last part, and that's what the best students will recognize, actually going, I can give more information here, I can actually describe the way it changes, and that's what you'd be looking for in the best answers here. Okay. So the last part of the mechanics section is looking at some forces and resultant forces, those kind of thing, which should have been fairly straightforward. Okay, so we've got a glider with 4 different forces acting on it, and they've been very nice to you. They're all perpendicular to each other already, which is unbelievably nice, but anyway. So what we're going to do is we want to first show that the magnitude of the resultant force is about 6,100 newtons. So the first thing we need to do is essentially simplify this, so work out what the resultant force is horizontally and the resultant force is vertically. So that's what you can see happening here. So this is the horizontal one. So we've got this much to the right, this much to the left, giving you 6,000 overall to the right. And we've got this much upwards, this much downwards, giving you 1,000 as a result upwards. And then those two are perpendicular, so we need to use some Pythagoras, put the numbers in, and we end up with a number which is approximately 6,100. Fairly straightforward. Even in show that questions, you still need to give answers with units. Hopefully that's something that's always done. We want to find the angle between this resultant force and the horizontal. So you can use sine or cosine, but given the values you've been given, it's much easier to use tan. So if we want tan of theta, that's going to be the opposite divided by the adjacent, giving us a value of 9.4623, blah, blah, blah. You could give this to 4 significant figures, because you can assume that these are 4 significant figure numbers if you want to, or you can give it to 2 if you assume that these are essentially 1 significant figure. So either of those was acceptable. Okay, so then calculate the resultant acceleration of the glider in the diagram. So the key to this was actually working out what the mass was, but given that you've got the weight force and you're on Earth, that's fairly straightforward. And then just using the simplified version of Newton's second law, you've got the force, you calculated it in part 1, you've got the mass now, and you can calculate what the resultant acceleration is. Okay. Alright, so let's have a look at the final part of this question. So we've got that the glider climbs a vertical distance of 600 meters. And this question wants us to calculate the gain in GPE. So this is really straightforward. You've got the weight force already, or mg. You've got the height, therefore you've got what the change in energy is. Nice and straightforward. Then it wants us to work out the percentage of efficiency of the system. So it told us above we've got the power input of 320 kilowatts, and we've got it over a time of 55 seconds. So the way I did this was working out what the useful power was, so taking the amount of energy we calculated above and dividing it by the time gives us the useful power, and then useful divided by total input times 100 gives us the efficiency. I could also have turned the input power into an input energy by multiplying it by time and then doing the efficiency with energy. Either way gives you an answer of 22%. So either way is fine. So that concludes this mechanics section. This question, loads of you got 11 out of 11, which is really good. Next section, we're going to look at the materials and waves part of this exam.